Okay, so there were questions about what the signal here is. So this is a free induction decay signal. So basically, just we created the spin magnetization on the XY plane, a transverse magnetization. And then under the action of the B0 field, there is a free precession, okay? And this free precession occurs at the Larmor frequency omega 0. And then the signal decays within a time scale T2 star, which is just the time where all the spin population seeing different Larmor frequencies in the homogeneous magnetic field will be somehow averaged to 0. Okay, the collective signal. And if you want, we can do a little bit of mathematics about that. It's not super complicated.
There was one more question.
Yes, please.
Like when you turn the field and when they start reversing their direction, so how fast they can come back, and is there like any acceleration, deceleration time involved?
No, this is coherent, so this can be done very quickly. So basically, just the drive, the intensity of the drive here. It's the duration of your pulse pi, which is just determined by the B1, the amplitude of the B1. But this, you can put a lot of power there, the power you have. So indeed, what you want to do experimentally is to have all those pulses as short as possible. But this is not a problem because up to a given point, but because in this pulse sequence, all the information is obtained during the free evolution of the system. When you are free, when the spin is not affected by the amplitude of the driving field. And it's exactly this idea that we'll try to implement with the NV Center and discuss the different contribution for T1, T2 star, and T2. Okay? So just to conclude the lecture for this afternoon, I would like now to just describe very quickly something, of course, that has made magnetic resonance very famous. It's the application to imaging. And remarkably, the application to imaging, you will see it's a very simple idea. It's so simple that you may ask yourself, why people who were very clever in understanding the behavior of spin didn't thought about that. That's really something quite fascinating to have this idea. And there was a set of people, different people that contributed to the emergence of imaging with magnetic resonance. Among them, two got the Nobel Prize of Medicine 20 years ago. And I will try to explain very quickly how this works. So suppose now, let's start with a spin distribution. So what you want to do is I take this bottle, okay, and I imagine that I want to measure the spin distribution along this transverse direction here. So how can I do that? So this is my bottle, okay, this way, okay. And what I will do now, if I have a homogeneous magnetic B0 field, all the spins here, provided the point we discussed previously, will produce a given resonance signal here. Okay, at this frequency here. Sorry, I shouldn't. Everyone agrees? The contribution of all the spin along this direction here will be the same, all producing the same resonance frequency. Now what I will do is I will apply along this direction a gradient of the magnetic field. But the magnetic field is still pointing in this direction. Eh? This is the z direction. Okay, so but I will put a gradient in the x direction where I want to measure the distribution of the spin. And of course, when you're close to the bottle here, we have less spin, and then progressively you can imagine that you have this dome shape we have the spatial distribution of protons. But now we measure it along this direction. So I've set now a gradient of the magnetic field in the z direction. What I do then, what will be the resonance signal? You see that the resonance signal is, of course, gamma B0 plus now gamma x time the gradient of the static magnetic field along this direction. This tells me that I have established a linear relation between omega and the position along this direction. So I can now have a signal that somehow will be like that. It will be the number of spin taken into account this projection. Of course, when I look from here, I have not much spin here, and then progressively it becomes broad. There's more and more spins up to a point where I'm in the middle of the bottle, then I see a constant homogeneity. It would be like something like a square vanishing progressively when I'm on the wall of my bottle. Do you see what? So basically what I do, from this signal, I have the projection of this, and if I know exactly the gradient of the magnetic field, then it's perfect, because I can deconvolute from that and get the spatial distribution of the spins along this axis. So it's remarkable. What you do is that you encode using the gradient of the magnetic field, you encode the position x in this direction on the frequency, on the resonance frequency of the spin. And then by just measuring how many spin are the intensity of the magnetic resonance signal, you measure the number of spin at a given position x. This is simply this experiment. That's remarkable. So I can do that, for instance. This is just a trick. You can think a little bit for a while about, suppose now I have a kind of distribution. So it can be like that, let's say. Okay, I have 4 bottles, or 3 bottles, or whatever, like in the game. And now I want to detect that. And how I can do that? The idea would be to apply a magnetic field gradient in different directions. The magnetic field is still like that. But the gradient, you can apply it like that using external coils. So imagine you have a lot of coils around the system, and you can apply your gradient how you want. Like this, like this, like this, like whatever. Okay? And so now I will have, just along this signal, I will have different frequencies. Okay? And for a given direction of the gradient of the magnetic field, I will record different profile of the resonance signal. And for instance, if I use 4 projections, 4 directions of the magnetic field, I detect this, suppose I have this signal. And now I want to determine which is the good one. It's a guess. You have different ideas around this. You can think, and I give the answer tomorrow morning. Okay? The answer will be given tomorrow, or I can do it now. So who is for 1? Who is for 2? Who is for 3? Who is for 4? No one? Who is for 5? Who is for 6? And who is for 7? You see the point? You see? So I have this. For instance, suppose like now I do that with the same bottle. Okay? Like this. Suppose I apply my magnetic field gradient in this direction. What will I see? I will see here a signal from here to here 2 times, and 1 time here. So that will be a signal with 1 peak, and a signal with the other peak associated to this bottle, a little bit further away. But this will be 2 times the amplitude of this one. Okay? Do you agree with me? Because I have 2 bottles when I do this and this. So I have a signal like 2 peaks and 1 peak. That's if I apply the magnetic field like that. Okay? Suppose I apply it like that. They're the same. I will have 2 peaks and 1 peak. Okay? Now I can also apply it like that. And then there will be 1 peak like that, and this will project onto this direction. But that will be 1 peak and the higher 2 peaks, okay, but the other one. And I can also do it like that, and that's quite interesting because if I do it like that, I will see 1 peak here, the 2 peaks going there, and another peak here that projects in between. Okay? And I will see 3 peaks in that direction. So that tells me that in this direction, if I do apply the magnetic field in this direction, I get the symmetry of the system. So I can play with that. And if you do that, then you can somehow use this information to put the signal here, you see? Like this and this and this and this and this. And then somehow you get the projection. Okay? And you know that here you will have something which is twice the intensity. Okay? And this and this and this and this. And basically you can convince yourself that it's something associated to this, this, and this. So it's something exactly what I showed you. Okay? So the signal I got, it's exactly the good one. And you can say that there are nevertheless some ghost resonances that appear here and here, which are weaker, and those are somehow a parasitic contribution. Okay? But at least you know that the configuration I show on the table here was exactly the one that produced this signal. Okay? Do you agree with me? So you can do that, and that's also one important feature of magnetic resonance imaging, of MRI, because that can be done mathematically. And you can also somehow get rid of those ghost images here using what is called an inverse Radon transform. It's something like a kind of Fourier transform adapted to this situation. But somehow the idea is you want to reconstruct the shape of a 3D object, and that can be done by taking slices. And from different slices, you can reconstruct the 3D shape, okay, using different projection. And that was actually invented for the radar. So all these techniques came from the radar. And because, of course, what you want to do in radar, you have station on the ground. Those emit radio waves, radio frequency signal up to the object you want to detect, for instance, an airplane. There will be echo signal. You catch the echo signal, and using the information from different radar states coming from associated to different radio frequency, and you somehow tune them by changing the frequency. You recognize each signal coming from each station by a different frequency, then you can reconstruct the plane and get information where it comes from. So it's exactly, that was, all those techniques were actually developed for the radar, for radar. And somehow all these people that invented NMR, it's something that is well known also, they were working for the development of radar during the Second World War, and after that they used somehow all their knowledge to develop the magnetic resonance technique in the lab for their own purposes. Okay, so now, of course, this was a very important tool, and it has been now implemented currently in hospitals, where basically you will look at the protons in water, and you use the fact that the water content of a diseased cell will be different than that of a healthy cell. Okay, and this is what you will do, for instance, to investigate if you have some disease or problem somewhere. Okay, and the resolution, of course, like that you can achieve, is of course limited by the amplitude of the gradient. And to have a gradient as high as possible for the magnetic field, you use superconducting magnet. So one of the, usually that's machine for magnetic resonance imaging, where you have here superconducting magnet, and the patient is integrated inside. And after that, in this machine, you have a system that turns the coils, which produce an awful noise regarding these issues. And here, if you see here, there is something here, just because if there is any problem with a superconducting magnet, of course, it heats up, and the helium that is required to get to the low temperature required for the superconducting magnet then immediately evaporates, so you need somewhere to flow the helium out, and this is usually what you have here. You have a host system, exhaust system, to prevent the quenching of if the quenching of the superconducting coils appear, then it heats up, not superconducting anymore. Temperature rise very quickly. All the helium goes to gas, and of course you have to put an exhaust, otherwise everything explodes. You can do a lot of developments with that. For instance, what was invented, something you've seen many, certainly images associated to that. It's what called functional medical imaging. So for instance, you detect blood oxygenation using paramagnetic tracers. So we'll introduce gadolinium, for instance, ions. These gadolinium ions will actually modify the T1 time. It will shorten them because there are interaction with the ions that modify the T1 time, and you quench the signal, the magnetic resonance signal. You decrease it very significantly, and that is a way to measure somehow the paramagnetic tracer and to see how they evolve. And this is, for instance, how you can do some image of living part of your body, like, for instance, the brain, and seeing when you speak, what do you activate, and do those kind of fascinating images that help really greatly the development of neuroscience. In France, for instance, close to Saclay, the Center for Atomic Energy used all his savoir-faire, all his technical knowledge on the development of superconducting magnet for particle accelerators to implement one of the most powerful imaging center for MRI, which is called Neurospin, with the idea that you can really image brain and see neurodisease and those neuronal disease, those kind of things, how it occurs, or you can see language apprentissage, for instance. All this can be investigated there. Up to a given limitation, it's the spatial resolution. And the spatial resolution is, of course, set by the gradient, and typically now they are a little bit below the millimeter range. This is enough for certain application, not enough for many other application. For instance, and one of the goals, for instance, where people have been working quite hard, is to use this kind of topic to see, for instance, if that can be applied for using NV centers. Again, I will come back to that, but there was a very nice development from my colleague with this idea, is to use, again, the same idea of a gradient of magnetic field that was done by colleagues in Thales, where you can do real-time spectral analysis of a signal. And this is, all, again, very important for all kind of recognition using radar techniques. So I will explain a little bit the implementation of this idea for other purposes, but again, how you can use the spatial encoding to analyze a signal. And it's exactly what is done, this kind of thing. There is a great also interest in doing NMR, not with big magnetic field, but on we're using small magnetic field that you can make with coils and reasonable current in coils. And this is, for instance, a French company, and the same is being developed in the US, for instance. But basically, the idea is to use very low magnetic field, below 10 millitesla, that you can easily produce with magnetic coils, and nevertheless make a kind of MRI systems that can work with approximately the same resolution as the one that you can achieve with those machines. And what is really great is that basically there's a lot of mathematics hidden. So you get signals, and after that, using a lot of clever transformation, mathematical transformation, like wavelet analysis, those kind of things, you try to retrieve the signal with a very noisy basis, but the noisy somehow is associated to the magnetic field. So if you map very carefully the structure of the magnetic field, then somehow you can improve very significantly the signal-to-noise ratio. That's a little bit the idea. So there's a lot of development, for instance, about implementing these NMR techniques at low field, using also data analysis treatment and very clever mathematical developments to get the signal out. Okay, so I would just like briefly to conclude the lecture for today, this morning and this afternoon. So what I wanted to show, basically, that NMR was first invented as a spectroscopy tool. It was used to measure the gyromagnetic factor of nuclei, and it has been also very successful for chemists to understand the structure of molecules. And this is certainly a very nice development. It has also been used also as a very important tool for solid-state physics. I should have mentioned that. For instance, the first demonstration of superconductivity was obtained using NMR. Why? Suppose you get now two electrons. You know that superconductivity comes from the binding of two electrons, for instance, with phonon in BCS theory, and that will create a Cooper pair. But this is now two electrons. So if I measure the NMR signal of that, I should see the spin of the two electrons in a way where they are, for instance, in the singlet state, total singlet state, or to produce the condensate of the Cooper pairs. So then I will see a clear difference due to the binding of the electrons in Cooper pairs compared to a single electron in the metal, for instance. So that has been very important, and NMR has been routinely used also to investigate the interior of a superconductor. You know that and I will explain that a little later on, due to the Meissner effect, the static magnetic field cannot penetrate a superconductor. So if you now have the protons inside your superconductors, they will see a screened magnetic field. So somehow you can investigate by, for instance, a kind of MRI technique, how the protons of your system will behave. And that's very important to understand the physics of the superconductor. So really, there's a lot of applications where also in solid-state physics, we have been able to use the technique coming from NMR, either use to nuclear spins or to electronic spins also, to understand really the physics of the system. And that's also very important. So it's really give you a handle on the electrons in the system. Importantly, NMR, it's an ensemble measurement, and its sensitivity is limited by the difficulty to prepare a well-defined quantum state. We rely on a thermal equilibrium. And we will see that how this can be somehow, we can circumvent that limitation, this bottleneck, by some pumping mechanism that will allow us to prepare to beat the thermal equilibrium. Okay, another point also, maybe more technical perhaps, but the calculation we did for the resonant interaction between the spin 1/2 and the oscillating magnetic field is general. You can adapt it, and for instance, this is exactly the tool for if you want to describe the interaction of a two-level atoms with ground state and excited state with an oscillating electromagnetic wave. It's the same calculation. You simply have to change a little bit the first equations, and basically you apply the same trick and you will get the same results. So that's why the block vector is also very useful if you want to describe, for instance, how a two-level atom interacts with an electromagnetic wave. And perhaps another more like technological consideration. NMR was really invented, I'll show you the work from Habi and others, as a fundamental research tool. And nevertheless, after that, very quickly, thanks to engineers, we have been able to exploit the precision, the accuracy, to develop instruments you can purchase an NMR spectrometer, you can purchase a nuclear imaging machine, MRI machine, and also you can refine reconstruction methods like Fourier transform, radon transform, and this also has been very important. So it has become now really an essential tool. But the time frame it takes to go from the first discovery by Habi at the end of the 30s to really first practical developments. Brucker, for instance, the NMR spectrograph from Brucker, I think, came out at the end in the 60s. It's something like 30 to 40 years. So it takes 30 to 40 years between a discovery or fundamental research to translate into a technical development. A real technical development, something that's really put on the market, that has all the features that people want. That's the time scale. Perhaps can be 20, can be, but there's very little experimental breakthrough, a technical breakthrough that are below this 20 years time scale. And this is something when you go, for instance, for the development of quantum technologies, explaining that to people that are funding the technical development is rather difficult. So it takes 20 years. And what the money you invest now in fundamental research, that will produce outcomes, and you don't know which outcomes 20 years later. That's not easy to explain. But I think if you do that, I think if you need at one point to explain this to people, I think nuclear magnetic imaging is a nice example. Nuclear magnetic MRI was people didn't thought that any kind of the magnetic resonance principles could be used to do imaging for medical purposes. And at the end, the story that just a little before his death, Rabi, who invented magnetic resonance, had to go to hospital, had this kind of medical exam in this MRI machine, and told the doctor, you know, I invented magnetic resonance, but I never have thought that this could have led to those kind of features. And exactly what perhaps need to be explained. Investing money in science, the outcome will be 20 years. Unfortunately, this is not the time frame for a politician. Politicians want to invest money and get the feedback, get benefit during the time where he is of his mandate, and this is a difficulty. Especially now in the context of quantum technology, this is commonly a problem, and we are facing that every time when we discuss with some people. Okay, we stop here today, and then tomorrow we really describe the NV Center.
All right, so let us thank him very much. So today's program ends here, and tomorrow we will begin at 10 o'clock. Same place, same time.
So really tomorrow we start with diamond, okay? And that's what and we start with diamond, and we try to explain what is the structure of diamond, why diamond is maybe interesting, and it's interesting due to its defects. And we try to explain that, and then we try to make perhaps what you learn in solid-state physics, the block function for electrons. I will try to explain why this is not appropriate, why we need another very different approach to describe the physics of a point defect in a solid. That's the purpose of tomorrow's talk, and then we'll continue on the NV centers afterwards. Good?